something strange is happening at the edge of our solar system. A mysterious visitor, an object from another star, just did something that has astronomers scratching their heads. It didn't just fly by. It broke apart. But not in the way we'd expect. It's like finding a message in a bottle, only the bottle shattered into 1,000 pieces right before our eyes, and the pieces are acting weirdly. This isn't just another rock from space. This is 3IATLAS, and connecting the dots of its bizarre journey reveals a picture that might change how we see the universe. So, let's rewind a bit. On December 28, 2019, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a robotic observatory in Hawaii designed to spot incoming space rocks, flagged a faint fuzzy object. Initially, astronomers thought it was just another comet from the outer reaches of our own solar system, a lonely traveler from the Oort cloud. They gave it a standard comet designation, C219 Atlas. For a few months, everything seemed normal. It was getting brighter as it approached the sun, just as a comet should, as solar radiation heats its surface and causes ice to sublimate, creating a glowing coma and tail. It was on track to become one of the brightest comets in decades, a potential naked-eye spectacle for the northern hemisphere. Hype was building, but then things started to get weird. In early April 2020, instead of continuing its spectacular brightening, the comet suddenly began to fade, rapidly. Observations from the Hubble Space Telescope confirmed our worst fears for the celestial show. The comet had disintegrated. Its single nucleus had broken into multiple smaller fragments. While comets do break up sometimes, especially on their first trip near the sun, the way Atlas did it was peculiar. And that's when astronomers took a closer look at its path, its trajectory through our solar system. The calculations revealed something astonishing. Its orbit was not closed, not a long stretched-out ellipse like the comets from our own Oort cloud. It was a hyperbolic orbit. This meant it wasn't bound by our sun's gravity. It was moving too fast. It had come from somewhere else entirely, from interstellar space. This changed everything. The comet was redesignated 3IATLAS. The I stands for interstellar, and it was only the third such object ever detected. The first, you might remember, was the bizarre cigar-shaped Oumuamua in 2017, which accelerated away from the sun without any visible tail, leaving scientists baffled. The second was to I Borisov in 2019, which behaved much more like a typical comet, giving us our first real glimpse at the chemical makeup of a comet from another star system. Now we had a third, and this one seemed to be a hybrid of the two. It looked like a comet, but it behaved erratically, much like Oumuamua. It was as if the universe was deliberately sending us puzzle pieces, each one stranger than the last. Oumuamua was a fast-moving rock that defied our models. Borisov was a relatively normal comet, just from far away. With 3IATLAS, it was something in between, a fragile messenger that couldn't even survive its first close encounter with our star. Let's dive into the specifics of what makes 3I Atlas so unusual. First, its speed and trajectory. Like Oumuamua and Borisov, it entered our solar system on a path that could only originate from outside. Its velocity was so high that our sun's gravity could bend its path but never capture it. It was always destined to be a one-time visitor. But when we traced its path backward, into the interstellar void, we couldn't pinpoint a specific star system it came from. It was a true cosmic orphan. More perplexing was its composition and behavior. Initial observations suggested it was a carbonaceous chondrite, a type of primitive body rich in water, ice, and organic molecules. It was shedding gas and dust, forming a coma, which is classic comet behavior, but the rate of its activity was unstable. It experienced sudden outbursts of brightness long before it got close enough to the sun for water ice to sublimate efficiently. This suggests it was rich in more volatile ices, like frozen carbon monoxide or carbon dioxide, which turn to gas at much colder temperatures. This is interesting because it tells us something about where it formed, likely a very cold, distant region of its home star system. But the real mystery began with its disintegration. As it approached the orbit of Mars, still more than 160 million kilometers from the sun, it just fell apart. Hubble's sharp vision revealed not one, but at least 4 distinct fragments, each enveloped in its own little coma of dust and gas, all continuing along the same path like a ghostly funeral procession. Why did it break up so far from the sun? Most sun-grazing comets that disintegrate do so much closer, where the sun's gravitational tidal forces and intense heat are strong enough to rip them to shreds. ATLAs broke apart where the sun's influence should have been relatively gentle. It was as if the object was incredibly fragile, barely held together. Some scientists proposed that maybe the comet's nucleus was spinning so fast that it just flew apart from centrifugal force. Others suggested that pockets of supervolatile ices beneath the surface heated up and exploded, like popping a champagne cork, shattering the nucleus from within. But what if we're not seeing the whole picture? What if we've been looking at all these data points, the hyperbolic orbit, the strange composition, the premature outbursts, the fragile disintegration as separate, random events? What happens when we try to connect the dots, when you lay out all the pieces of the 3I Atlas puzzle? A fascinating And frankly, a much weirder picture begins to emerge. It's a picture that pushes the boundaries of what we consider a natural object. Let's start assembling these observations, not as individual facts but as a sequence of events. First, we have an object that travels for millions of years through interstellar space. It survives the harsh environment of the void, cosmic radiation, extreme cold, and a complete lack of external forces. Then, it enters our solar system. As it gets closer to our sun, but still in the freezing outer reaches, it begins to show signs of activity. Not just a gentle awakening, but sudden energetic bursts of gas and dust. This suggests that the release of energy wasn't a smooth, uniform process like an ice cube melting. It was more like a series of controlled, or at least compartmentalized, releases. Think of it less like a single block of ice and more like a package containing multiple, smaller ice packs, each rupturing at a different time. Then comes the main event, the fragmentation. It doesn't explode in a chaotic burst. It splits into a few distinct primary pieces. And these pieces don't just tumble away randomly. They continue along the original trajectory, each creating its own mini-coma. It was an orderly disassembly. It's this sequence, the long journey of stability, the sequenced bursts of activity, and the structured fragmentation that starts to look less like a random act of nature and more like a process. Now, let's add another layer. Compare this again to Oumuamua. Oumuamua showed no outgassing, no coma, yet it accelerated away from the sun. The leading hypothesis for that was outgassing of hydrogen ice, which would be invisible to our telescopes. Another, more controversial idea was that it was a thin, lightweight object being pushed by solar radiation, a solar sail. Now look at 3I-ATLAs. It was also fragile, also behaved strangely, but in a completely different way. It actively shed material. What if Oumuamua and 3I-ATLAs are two sides of the same coin? What if they represent two different types of interstellar probes or messengers? One designed to be robust and stealthy, the other designed to be fragile and to release its contents. Let's be clear, this is pure speculation. The overwhelming scientific consensus is that 3I Atlas was a natural comet, albeit a very strange and fragile one. Its behavior, while unusual, can likely be explained by a combination of a unique composition, a rapid spin, and thermal stresses. Nature is perfectly capable of producing things far weirder than we can imagine. The universe doesn't have to play by our expectations, but for the sake of exploring the unknown, let's follow this thought experiment to its logical, if unsettling, conclusion. If you were to design an interstellar probe meant to deliver something to the inner part of a star system, how might you do it? You'd need it to survive a long journey, so you'd encase it in a protective shell. This shell would need to be made of materials that are common in the universe, to look natural, like rock and ice. To get your package to the right place, you might need to make small course corrections. Perhaps sudden bursts of outgassing could act as small thrusters, subtly adjusting the trajectory. And finally, once it reaches its destination zone, say, the habitable zone of a star system, you would want it to release its payload. A catastrophic but controlled disintegration would be an effective way to do this. The probe wouldn't need to land. It could simply break apart and scatter its contents, perhaps microscopic organisms or complex organic molecules, a process known as panspermia, into the inner solar system, where they might one day seed life on a receptive planet. In this scenario, 3I Atlas wasn't a failure that broke up too early. It was a success that executed its mission exactly as planned. The sequenced bursts were course corrections. The fragmentation was payload delivery. The choice of a highly volatile composition wasn't an accident. It was a feature, ensuring the object would fall apart at a specific distance from the star, triggered by a precise temperature. This idea, of course, sounds like science fiction, and it's important to stress that there is absolutely no direct evidence to support this. It is a hypothesis born from connecting the dots of anomalous data in a way that creates a narrative of intent. But the history of science is filled with moments where extraordinary claims, initially dismissed as fantasy, eventually lead to new frontiers of understanding. We once thought the Earth was the center of the universe. We once thought our galaxy was the only one. Every major leap in our cosmic perspective has come from confronting anomalous data points that just don't fit the current model. The story of 3I Atlas is not just about a disintegrating comet. It's about how we interpret the unknown. Do we see its strange behavior as a random fluke of nature, a one in a billion cosmic coincidence? Or do we dare to ask if it's a sign of something more? Is it possible that the patterns we see in its demise are not just our human tendency to find order in chaos, but a genuine signal that we are only just beginning to decipher? The fragments of 3I Atlas have long since dissipated, their dust and gas scattered to the solar winds, never to be seen again. But the data it left behind, the questions it raised, continue to orbit our scientific consciousness. This strange visitor didn't just give us a fleeting light show. It gave us a profound mystery. And in science, a good mystery is often the beginning of the next great discovery. As we continue to scan the skies, what other messengers might be on their way? And will we be ready to understand what they're trying to tell us? What does it truly mean to connect the dots? When we look up at the night sky, We see a canvas of random, twinkling lights, but our ancestors saw more. They saw stories, heroes, and myths. They connected the dots and created constellations. This innate human desire to find patterns, to weave narratives from seemingly unrelated points, is at the very core of scientific discovery. But it's also at the core of our greatest speculations. Today, we're reapplying that same ancient practice to one of the most baffling celestial objects ever observed, 3IATLAS, also known as BOR. And when we start connecting the dots surrounding this interstellar visitor, the picture that emerges is, well, it's strange. Very strange. It forces us to question whether we're looking at a random collection of cosmic coincidences or the faint outline of something far more profound. Let's start with the first dot, Oumuamua. Remember that one? The first interstellar object we ever detected. Back in 2017, it was bizarre. Cigar-shaped, or maybe pancake-shaped, tumbling end over end. It accelerated away from the sun without any visible tail, defying our understanding of comets. The leading scientific explanation settled on it being a nitrogen iceberg, a fragment chipped off a Pluto-like exoplanet. It was a neat theory, but one that required a whole new class of object we'd never seen before. A lot of astronomers were satisfied, but a vocal minority, including Harvard's Avi Loeb, proposed a more radical idea that Oumuamua's strange acceleration was caused by a solar sail, an artifact, a piece of extraterrestrial technology. The scientific community largely dismissed this as sensationalism. It was an interesting thought experiment, but there was no definitive proof. Oumuamua was a single anomalous data point, a lonely dot on a vast empty chart. Then, just 2 years later, in 2019, the second dot appeared, 3IATLAS, or Comet Borisov. At first it seemed like the perfect counterpoint to Oumuamua. It looked and acted exactly like a comet from our own solar system. It had a visible coma, a tail of gas and dust, and its path was perfectly explained by gravitational forces and outgassing. The astronomical community breathed a collective sigh of relief. See, Oumuamua was the weird one. Borisov is normal. This is what interstellar comets are supposed to look like. It reinforced the idea that our corner of the galaxy isn't all that different from others. Case closed, right? But this is where our story truly begins. Because when you look closer at Borisov, the normal explanation starts to fray at the edges. The first hint of strangeness was its composition. Using the Hubble Space Telescope, astronomers got a good look at the gas spewing from Borisov. They found it was incredibly rich in carbon monoxide, far more than any comet from our own solar system. This suggested it formed in a very different, much colder environment than our own comets, likely in the outer disk of a red dwarf star system. Okay, different, but not impossible. It's an interstellar object, after all. It's supposed to come from somewhere different. But then came the second, much stranger observation. As Borisov got closer to the sun, it did something completely unexpected. It fell apart. Not just a little bit, but catastrophically. It fragmented into multiple pieces and then essentially vaporized, disappearing from our view. Now comets from our solar system do break up. It happened, but Borisov's disintegration was extreme. And it happened quite far from the sun, where the thermal and gravitational stresses weren't at their peak. It behaved less like a solid icy body and more like a loosely packed snowball. This is dot number 2. We have an object that, on the surface, looks like a normal comet, but has a bizarre chemical makeup and a structural integrity that seems almost comically fragile. It's as if it was designed to look like a comet, but wasn't built to last. This is where the speculation starts to get bold. If Oumuamua was an anomaly for being too sturdy and behaving too strangely, Borisov was an anomaly for being too fragile and behaving too predictably, right up until it didn't. Some researchers, looking at these two data points, have started to ask a provocative question. What if they are related? What if we're not looking at two random, unrelated visitors from deep space? What if we are looking at two pieces of a larger puzzle? Let's connect the dots. Dot 1. Oumuamua, a high-strength object with no visible outgassing that accelerates in a way suggestive of a solar sail. Dot 2. Borisov, a low-strength object, rich in specific chemicals, that looks like a comet but disintegrates unexpectedly. The conventional view is that these are two entirely separate natural phenomena. One is a nitrogen iceberg. The other is a fragile carbon monoxide-rich comet. Their arrival within 2 years of each other is pure coincidence. But what if it's not? This is where we enter the territory of what some are calling non-natural origins. Let's entertain a hypothesis, purely for the sake of argument. Imagine an advanced civilization wants to send probes to other star systems. A big, obvious ship like the Starship Enterprise would be easily detectable. A better strategy might be stealth. How do you hide a probe? You disguise it as something common, something natural. You disguise it as a comet. In this speculative scenario, an object like Borisov isn't a natural comet at all. It's a delivery system. It's a mothership or a carrier designed to travel across interstellar space. Its fragile, loosely packed structure and its rich carbon monoxide coma aren't bugs, they're features. The coma acts as a perfect camouflage, hiding whatever is inside. and its tendency to disintegrate. That's the deployment mechanism. As it approaches a target star system, the carrier vehicle breaks apart, releasing its payload. And what might that payload be? This brings us back to Oumuamua. What if Oumuamua wasn't just a random rock or a nitrogen iceberg? What if it was the payload? What if Borisov or an object like Borisov was the vehicle that deployed it? In this scenario, Oumuamua is a scout, a small durable probe designed to survive entry into a star system, gather data, and use the star's own light to accelerate on its way to the next target. This would explain its weird shape optimized for travel, not for geology. It would explain its non-gravitational acceleration. It's a solar sail. And it would explain its timing, arriving shortly before or after its carrier passed through. This idea fundamentally reframes how we view these objects. It suggests we haven't just been visited by two interstellar oddities. It suggests we may have witnessed a technological deployment event. The dots, once connected, shift from being random astronomical curiosities to potential evidence of a coordinated, intelligent strategy. Suddenly, other overlooked details snap into focus. Why did Borisov disintegrate so far from the sun? Perhaps to deploy its payload at the optimal trajectory before being destroyed by solar radiation. Why was Oumuamua tumbling? Perhaps its propulsional guidance system had malfunctioned after deployment. This is, without a doubt, a giant leap of speculation. It's a hypothesis built on just a few tantalizing data points. The scientific community is deeply divided. Most astronomers would argue, and rightly so, that we should always default to the simplest, natural explanation. This is Occam's razor, the idea of a nitrogen iceberg and a fragile comet, while requiring new theories, is still vastly simpler than invoking extraterrestrial engineers. They see randomness, a statistical fluke of two very different, very strange objects happening to visit us in quick succession. But a growing number of thinkers argue that sticking rigidly to natural explanations can sometimes be a failure of imagination. When something doesn't fit any known natural model, perhaps it's because it isn't natural. They argue that the non-natural hypothesis, while extraordinary, actually explains the bizarre characteristics of both Oumuamua and Borisov more elegantly than to separate ad hoc natural theories. In their view, it's not about seeing aliens behind every rock. It's about acknowledging when the data is so strange that it warrants considering all possibilities, no matter how unsettling. If this speculative connection is true, even in principle, it marks a turning point not just for astronomy, but for humanity. It means the evidence of extraterrestrial intelligence might not come in the form of a "Hello Earth" (RADIO) signal from SETI. It might come as a series of quiet, subtle clues that we have to piece together. It implies that we might have already missed other clues, other dots that were dismissed as noise, instrument error, or one-off anomalies. It changes everything. It means we need to start looking at the sky not just as a collection of natural phenomena, but as a potential archaeological site, containing the artifacts of civilizations far older and more advanced than our own. This brings us to the ultimate question, the one that hangs over all of this. What do you see when you connect the dots? Do you see an incredibly rare, but ultimately natural, astronomical coincidence? Two unique visitors from other star systems, whose strangeness is just a reflection of the vast, unexplored diversity of the cosmos? Or do the connected points reveal something more? The faint, ghostly outline of a purpose, a design, evidence of extraterrestrial intelligence, hiding in plain sight? Is it all just a grand case of pareidolia or pattern-seeking brains imposing meaning where there is none? Or are we finally beginning to decipher a message that has been floating in the cosmic ocean all along? There is no easy answer. The truth is, we don't have enough data to be certain. But the debate itself is valuable. It pushes the boundaries of science and forces us to confront our place in the universe. So, what's your perspective? Do you trust the science that points toward exotic but natural explanations? Or do you find yourself leaning toward the possibility that we've witnessed something truly technological? Is it a story of rocks or a story of robots? Let me know what you think in the comments below. This is one of the biggest questions we can ask, and every perspective matters. Did we just witness a cosmic coincidence, or the calling card of an alien intelligence? Thank you so much for joining me on this deep dive into one of modern astronomy's greatest mysteries. If you enjoy wrestling with these big ideas and exploring the frontiers of science and speculation, please consider liking this video and subscribing to the channel. It really helps us continue to create content that challenges the way we see the universe. Until next time, keep looking up and never stop connecting the dots.